horizontal axis represents time and the vertical axis represents velocity. Now, you already know about the velocity time graphs from your O levels. So, for example, if there's some object traveling at, let's say, 5 meters per second for around 10 seconds, then its graph is going to look something like this. It's going to be a horizontal line which stays at 5 meters per second for 10 seconds, right? Let's write down the units on the axis as well, just so we're sure what units we're using. Now, if we look at the equation that defines this motion, it's simply velocity equals distance upon time, right? So if you know the velocity at which the object is traveling and you know for how long it's traveling at this velocity, you can easily figure out how far the object traveled, right? So all you would need to do is plug in all of the values into this equation over here and simply perform a calculation. So your velocity is 5, your displacement is an unknown, and your time is 10. So you would just do 5 times 10, which would give you 50 meters as your displacement, right? That's simple enough. And another way of thinking about displacement is the fact that it's just the area under this line over here, right? It makes a rectangle with the 10-second line, the velocity axis, and the x-axis. If you think about it, it's just a rectangle. And if you want to find the area for a rectangle, all you need to do is multiply its length by its breadth, right? So this rectangle is 10 seconds in length and it has a breadth of 5, which also gives you 50. And this 50 is the same as displacement, so it's safe to assume that the area under the velocity time graph gives us displacement, right? But if we think about the motion of this object, right? It had 5 meters per second velocity and that velocity never changed. So if we really think about it, the object was not accelerating at all. It had a zero acceleration. And a zero acceleration means that the object was not changing its speed at all. Its speed did not increase, its speed did not decrease as well. So this has all been O-level physics so far, and let's actually build upon this knowledge and talk about a case where the object actually accelerates, which is to say that its velocity increases or it can decrease as well. But let's talk about a general case over here, and let's label the axis again. The horizontal axis represents time, the vertical axis represents velocity, but instead of using numbers to represent values, let's just say that the object starts off with a certain initial velocity, we'll call it u, and it increases its velocity for a certain time, let's call this time t, and ends up with a velocity v. So the object starts off with an initial velocity of u, increases its velocity and ends up with a velocity of v after t seconds. So if I want to find out the acceleration of this object, because the object is accelerating, it's increasing its velocity as time passes by. If I want to figure out its velocity, its acceleration, I'll first need to figure out how much its velocity actually increased and then just divide it by the time it takes for the object to increase its velocity. So that's going to be fairly simple. All we'll need to do is subtract the initial velocity from the final velocity, which will give us the increase in velocity, and divide this by time. And so if you think about it, this is just the formula for acceleration, which you probably already knew. But let's just rearrange this equation, take the t to the other side and cross multiply it so that we get a times t equals v minus u, and let's add u to both sides, so we get v equals u plus at. Now this equation over here is what will be known as the first equation of motion, right? So you can use this equation if you know the initial velocity, you know how fast the velocity is increasing, and you know for how long this acceleration takes place. You can figure out what the object's final velocity is going to be. Now let's think about the displacement of the object. And remember that the displacement is simply the area under this graph over here, right? It's just going to be this area, but it's not a simple rectangle like before. So let's actually break it up. Let's think of this as a compound shape and break it up into a triangle at the top. So a right angle triangle at the top and a rectangle at the bottom. So if I can find this green area over here for the triangle, and if I can find this red area over here for this rectangle, and if I can add both of these areas up, I'll just end up with the displacement of the object. If I just add them up, I'll get the total displacement. So let's actually try and find out these areas over here. So for the rectangle over here, it's going to be fairly simple. It has a length of t and it has a height of u. So the area of the rectangle, it's just going to be length times breadth, which is just u times t, right? And then let's think about the area of the triangle over here for a second. So if you want to find the area of a triangle, you know the formula. It's half times the base of the triangle times its height. So let's think about the base of the triangle. It's just going to be this length over here, which is the same as t, which is the same as the length of the rectangle. But let's think about the height of the triangle. It's just going to be this length over here. And in order to figure this out, we'll need to break up what we know. So we know that from the horizontal axis up to this point over here, this height is represented by u, right? And from the horizontal axis all the way up to this point over here, this height is going to be represented by v. So if you want to find the height of the triangle, we can simply take away u from v and we'll have the height. So the base of the triangle over here, it's just time, and the height, it's going to be v minus u. Now let's think about v minus u. We've actually seen this before as well. We've seen it over here. And if I want to replace v minus u with a times t, I can do that because it's the same. V minus u equals a times t. So I'm just going to say that the area is actually just half times time times a t. And since I have two t's over here, I can just combine them so that I have half a t squared. So the area of the triangle is then going to be half times a times t squared, and the area of the rectangle, that's just ut. So if I add both of these areas up, let's call this total area. This is going to equal the displacement of the object. So let's just call it d, and let's add the areas up. So we have ut for the rectangle, so ut, and we have half at squared for the triangle, so plus half at squared. And so this is going to give us the displacement of the object. If we know the initial velocity, we know the duration for which the object is accelerating, and we know the value for this acceleration, we can figure out how far the object is going to travel, or which is just to say its displacement. So this equation over here is going to be known as the second equation of motion. Equation of motion. Right, there's actually one more equation of motion, and that equation of motion comes from the fact that we have time over here, right? What if we want to get rid of the time variable and just think about velocities, displacements, and accelerations? Get rid of the time. And so a very simple way of doing that would be to just find what time would be from the first equation of motion. So if I just rearrange this, I'm going to get t equals v minus u over a. So solving this acceleration equation for time gives me v minus u over a. And if I want to get rid of the t over here, the time variable, all I need to do is use this relationship and replace all of the t's with v minus u over a. So I would just end up doing something like this. I would get d equals u times v minus u over a plus half a, and then instead of the t I would have v minus u over a again, and then all of this squared because you're squaring the t over here, right? Now I'm not actually going to compute this formula over here, but think of this as an assignment for yourself and try and solve this and simplify this entire expression over here. And what you'll end up with is something like this. You'll have 2 times the acceleration times the displacement equals the final velocity squared minus the initial velocity squared. Now, if you look at this equation closely, there's no time variable over here. It's just acceleration, displacement, and velocities, the initial and final velocities. So if you don't know how long you're accelerating for, you can use this equation to figure out any unknowns that you have. So you'll just have to look at the question in front of you and extract the information that you have. Think about the information that the question is asking you for, and then decide which one of the three equations you would like to use. So this is going to be the third equation of motion. Now remember that these equations of motions are for the case that we've discussed, which is uniformly accelerating objects. So your object was accelerating at a constant rate, which is to say that it wasn't increasing, its acceleration was neither increasing nor decreasing, it was just a constant rate. So as long as you have uniform acceleration, you can use these three equations of motion to figure out any unknown. So let's just compile these equations over here and try and solve a question or two. So let's write down the three equations. The first one is going to be v equals u plus at. The second one is d equals ut plus half at squared. And the third one is just 2ad equals v squared minus u squared. Keep in mind that the variables that I've used over here, for example, v, u, and d, the alphabet for these variables might change depending on the book that you're using. Some books use S to represent displacement. Some books use Vf for final velocity and Vi for initial velocity. So that won't change the formulas, it will just change the alphabets that you're using to represent the same variables. Okay, so let's look at a question next just to get used to using these equations. Let's look at this example over here and try to figure out how we can use the equations to actually solve problems. So let's look at the question. It says a car traveling at a constant velocity of 5 meters per second starts to accelerate so that its velocity after 20 seconds is 12 meters per second. how far did the car travel during this acceleration? So they're asking us to find how far the car travels. Before you actually try and solve the question, it's always a good practice to write down the knowns and the unknowns in the question, right? So what we know is the velocity of the car before it starts to accelerate. So that's our initial velocity, which is 5 meters per second. We know that it accelerates for 20 seconds, which means that we know that our time is going to be 20 seconds. And we know that after the 20-second time period, it has a velocity of 12 meters per second. So that's going to be our final velocity. And since they're asking us to find how far the car traveled, what we're really looking for is the displacement over here. Now, this summarizes all of the knowns and the unknowns in the question. So we don't really need the text of the question anymore. So let's list down the equations from before. We had v equals u plus at. We had d equals ut plus half at squared, and we had 2 times a times d equals v squared minus u squared. Now, since we're looking for d and the stuff that we know is u, t, and v, we need to figure out which equation will give us the answer, which equation has the right knowns and the right unknowns. So a quick glance over the first equation tells us that it doesn't have d, so it's of no use to us right now. Let's move on to the next one, and it does have the d. So in order to find the displacement d over here, we'll need the initial velocity, which we know. We'll need the time of acceleration or the period of acceleration that we know as well. But we'll need the acceleration itself, which is an unknown. We don't really know what the acceleration of the car is. So let's move on to the next equation. And turns out the third equation needs acceleration as well. So we're at a roadblock over here. We're at a dead end. Unless we don't find A, we can't find D. So let's go back to the first equation and use it to find A first. We can do that because we only need V, which is final velocity. We know that. We need the initial velocity U. We know that as well. And we need T. We know that as well. So let's try and use this to find A. So V is 12, U is 5, plus A is the unknown, and T is 20. If we rearrange this, we get 12 minus 5 over 20 equals A, which is just 7 over 20 meters per second squared. So that's our value for A. Now that we know what A is going to be, we can use either the second or the third equations to find the displacement. Because now we have all of the knowns that we need to perform the calculation. So let's just use the second equation to solve this question over here. And in order to find the displacement, we'll need the initial velocity, which is 5, multiply that with the time, which is 20, and add half times the acceleration times the square of time. So we can actually just cancel out one of these 20s with the square and simplify the 20 with the 2 and get a 10 over here. So what we really need to do is 5 times 20, which gives us 100, and add to that 7 times 10, which is just 70. So if we just add them up, we get 170, which is our answer. Now, obviously, the answer is important, but what's more important over here is for you to understand the process that we just went through. So you need to identify what you know and what you don't know, and then look at the equations of motions and figure out how you're going to be using them to find your unknown. So this sums up the demo that I had prepared.